Okay, I think that's it for logistics. So let's go ahead and get started. So I won't do like a big recap of the previous lectures like I usually do. So I'll just mention last week, what did we cover? We talked about kind of optimal spectral expanders, the alone Bopana lower bound on kind of what the best eigenvalues you can get are. And then Shahar talked a little bit about actual constructions that achieve this bound called Ramanujan graphs. I think we mentioned that kind of random graphs turn out to be really good expanders, like almost Ramanujan graphs. Although we didn't prove this, this is a very complicated result. And Shahar also kind of went through the definition of what are called the LPS graphs, which are these kind of complicated algebraic Cayley graphs that achieve this, that are Ramanujan, that achieve like exactly this 2 root d minus 1 second eigenvalue. But these things are way too complicated to analyze, at least within this course. And so what we're going to see this week is some explicit constructions of infinite families of expander graphs that actually are simple enough to analyze. We'll actually go through the analysis of their bounds and their construction. We'll see 2 types. So maybe I should say kind of this week, explicit constructions. We'll see 2 types. We will actually see, today we'll be talking about, and probably going a little bit into Thursday, we'll be talking about an algebraic construction that is substantially simpler than LPS. So you don't have to be too scared by the algebraic portion of this. And then Thursday, and maybe going into next week, Shahar will talk about the zigzag product, which is basically a combinatorial way that you can build expander families. So we'll go through at least some of the analysis on both of these. So I guess before kind of jumping into the algebraic construction, there is one thing I want to mention, which is what do I actually mean when I say an explicit family of expander graphs? In particular, we're looking at some kind of infinite object. If I tell you that I want some kind of explicit construction of a finite object, you know, probably I just mean non-randomized, like you gave me the adjacency matrix or something like that. But it's maybe like not quite as clear what I mean by an explicit construction when I'm talking about an infinite family of graphs, right? Clearly, I can't just give you an infinite family of graphs. That doesn't make any sense. So what does it mean to be explicit? One definition that would maybe be the most natural is just that it's not randomized, that kind of each graph in the family is constructible. But in fact, there's kind of a very specific thing that explicit means, or kind of 1 or 2 things that explicit means in the literature. And we won't care too much about this, but I just want to prepare you for seeing, you know, if you go and try to read the literature, I want to prepare you for seeing these terms and at least kind of informally tell you what they mean. So let me kind of tell you 2 different types of what it means to be an explicit family of expander graphs or just of graphs to start out slightly more formally. So explicit families. So let's let GI, where I is indexed in like the natural numbers, be some infinite family of graphs. At this point, I don't really care if they're expanders. In the context of this course, of course, we'll want them to be expanders, but for here, it doesn't really matter. So let's let this be an infinite family of graphs. And let's say that GI is on Ni vertices, where Ni is going to infinity. Now, formally, you maybe want to guarantee that Ni doesn't grow too fast. Kind of depends on how you define things, but I'm going to be a little bit vague and not super formal. I just want to give you kind of the intuition behind these so that when you see them, you'll be equipped to kind of figure out exactly what they're talking about in a paper. So there are kind of 2 definitions of what it means to be explicit. So the first is we'll call, sorry, I guess I should say kind of informally, basically these will both be kind of not only that the graphs are constructible, but that they're somehow constructible efficiently. So if we actually want to use an explicit construction in a code or in some actual application, not only do we want them to be not randomized so we can actually agree on some kind of actual object, we'd also like them to be efficient somehow, right? We'd like our algorithms to run in polynomial time or whatever. So basically these two guarantees will be talking about kind of how efficient the graphs can be constructed. So the first one is called mildly explicit. Or weakly explicit. These things kind of vary a little bit in the literature, but it's something like this. So we call GI, let's say, mildly explicit. Basically, if it's constructible in polynomial time. If GI each GI is constructible in polynomial time. Now, you might reasonably complain that this isn't particularly well defined because I haven't told you what it's polynomial in. And again, this is something that depends on where you look in the literature. Sometimes it's defined to be polynomial in I, sometimes it's defined to be polynomial in Ni. You have to look at the specific paper, what they're defining. So just something to watch out for. So that's mildly explicit. More or less, it just says kind of constructible in polynomial time. The second is called strongly explicit. And this is actually a local condition. And again, I'm going to be a bit informal. But basically what it will say is that you can construct, kind of given a vertex in GI, you can construct its neighborhood really efficiently. So let me say, what do I mean by that? So, okay, we call GI strongly explicit or very explicit. Basically, if kind of given a vertex in GI, we can compute the neighborhood of V in polylog time, or polynomial time, maybe in the description length of the vertex. So this basically says that even if you maybe can't, if the graph is enormous and you can't maybe hold the whole graph in memory, or the graph is too big to construct, if all you want to do is kind of move locally from vertex to vertex, then maybe we can still do this efficiently, right? And why would you care about this? Well, a lot of the applications that we've seen have been about random walks on these graphs, right? So imagine you maybe have a problem and you have kind of n random seeds or something like that. And so when you generate like the random or n bit random seeds, so when you generate the kind of the corresponding graph, it's exponentially sized, right? It's a size 2 to the n. But what you want to do kind of with, the error reduction and other, many other applications is you just want to take a random walk on this graph. And what does that require? Well, when you're at a vertex V, what do you need to know? You need to know the description of V, but that's only n bits, right? Even though your graph is 2 to the n size, the description is only n bits. And if you can find all of its neighbors efficiently in poly n time, then you can actually, even though you're on an exponentially sized object, you can operate on it in polynomial time. So it's quite useful to have this kind of locally or strongly explicit behavior so that you can kind of take random walks on an exponentially sized graph still in polynomial time. So we won't go too much into applications that need this, but this is, was kind of crucial to a number of breakthroughs that use expanders and is an important property. Anyway, that's all I'm going to say about kind of what it means to be explicit. I think we're going to see the first construction we're going to see actually is strongly explicit. The one Shahar is going to talk about, I think the version we're going to give in class is mildly explicit, but there is a way to make it strongly explicit. We'll mention these things as we go on. But I just wanted to kind of give you a heads up to what these mean when you look out in the literature. So any questions, I guess, about what I mean when I say an explicit construction of an infinite family of graphs? If not, we'll move on to actually defining our algebraic construction.
Yeah, maybe I just add one thing on that. So here's one way I'm thinking about this definition. So think of the graph as having n nodes. So this mildly explicit, so they give you n as a parameter as an input, and you in polynomial in n time constructs the adjacency matrix of this graph, which is like an n by n matrix. So you need like poly n time to describe it. And then strongly explicit says, well, you don't need to construct the whole thing. I just give you an index for a row of this matrix, that's log n bits. Specify a row, in this row, let's say this graph has constant degree. So I give you data, I give you the index of its neighbor, like with the first one, the second one, the third one, and you spit out, the value of this neighbor, which is another log n bits. So because the inputs and the outputs are now log n bits instead of poly n bits, there is a chance of actually computing that in polylog n time. So this is strongly explicit.
Yeah. So I cheated a little bit. You are supposed to give, you're not computing the whole neighborhood, but you're given, the second, give me the second neighbor or the third neighbor or something like that, as Shachar said. That's right. Okay, cool. So let's go ahead and jump into our algebraic construction of expander graphs, strongly explicit family. So this is a construction originally due to Margulis. The analysis we're going to give of it is due to Gabber and Galil a little later on, but let's go through the definition first. So for all n in the natural numbers, let Gn be a graph on the following group, the Cartesian product of Z mod n, Zn cross Cn. So what is this? This is just tuples, AB, where A and B are in 0 through n minus 1. So this is the vertex set. This is, I think, a Schreier graph, which was kind of the generalized version of Cayley graphs that we mentioned earlier. This is just to say, kind of, to define the edges, I'm going to need to define a couple operators to act on this group, just matrices, really. So to help out defining the graph, let's define a couple useful helpers. We'll have the matrix T1, and this is equal to 1, 2, 0, 1. We'll have the matrix T2, which is just its transpose, 1, 0, 2, 1, but notationally it'll be a little easier to write T2 instead of T transpose. And then we'll just have the standard basis vectors. We'll have E1 be equal to 1, 0, and we'll have E2 be equal to 0. Okay, so this is all we need to define the edges. So then I'm going to say, kind of, for any vertex V in, by the way, I'll write this usually as Zn squared, just notation. So for any vertex V in Zn squared, what is V adjacent to? So we'll define V is adjacent to the following set. We have basically applications of affine shifts defined by the operators I just gave you. So T1V, T2V, T1V plus E1, and T2V plus E2. So that's 4, and then we'll also take kind of all of the inverse shifts. So we'll have T1 inverse V. So notice these are non-singular matrices, right? So we can take the inverse. T1 inverse V, T2 inverse V, T1 inverse V plus E1, and T2 inverse V plus E2. Okay, so then maybe I can
they call it minus E1 and in parentheses, so actually this is the inverse.
Sorry?
So I think this is not really the inverse. The inverse of this affine would be you first subtract E1 and then you multiply by T1 inverse.
It's not right. Sorry, not the. I meant the inverse of the just the matrices. You're right. Not the inverse of the affine operator.
No, you want the inverse of the affine operator, right? So that would be the reverse edge.
I don't.
If you take an operation going from node U to node V, then you need the inverse operation going from V back to U. So it's just the inverse. It's just the inverse operator.
So you're saying it should be minus E1 and minus E2?
It should be, well, it should be T1 minus 1 and then multiplied in parentheses V minus E1. But you want it to, as if when it's acting on the image, to give you better source where you started.
So, sorry, you're saying it's, okay, well, this is going to make things complicated.
But I don't think in the proof we ever actually use these inverse operators directly.
No, you don't use, yeah, you don't, which is why I didn't catch this, because you don't actually use it.
Yeah.
You're right that when you define it, you want to get back. So when I apply T, right, I want to be applying like T2 to E1. Sorry, so you want to be, so you're saying it's T1. So sorry, for the, hold up. Let's try to get this right before we move on.
Inverse, then parentheses.
Then we have
v minus e1.
Right, okay.
Yeah, and then the
So
second one.
then you're saying when you apply, right. Okay, because now when we apply T1 to this, right, we want to apply T1 to this plus E1.
No, T1 to that and then E1. Yeah.
Right.
You apply T1 to that and then E1.
Right, you want this.
You want to get the phi, yeah.
Right.
Yeah,
okay. Yeah, this will work, right? Because this is V minus E1 plus E1 is equal to V. Okay, so thank you. Let's try that again. Good catch. So this is T1 inverse.
No, this one is fine. The first one is fine because there's no E1.
These two are
fine. The second one is fine.
This is T1 inverse of V minus E.
Yeah.
There we go. This is T2 inverse of V minus E2.
Yeah.
Okay. Yeah, we won't really use the inverse operators in the proof, which is why I didn't catch this, but it is important to have things defined correctly. Thank you. Okay, yeah, so these are just the inverse, these are just kind of the inverse operations of the previous line. So like we were saying, if you compose them, you want to make sure you get out V again, which is what I just showed below. Okay, so there are a couple things I want to note about this graph. First of all, it's 8 regular, right? For every vertex, we're defining 8 edges. And then there are kind of 2 other things. And to see this, it's maybe instructive to look at kind of where 0, 0 maps to. What is 0, 0 adjacent to? Well, the first thing to notice is that, if you apply T1, 0, 0, you're obviously going to get 0, 0. Right, so 0, 0 is mapping to itself, which means I kind of lied to you. I should probably specify that self loops are allowed in this graph. So self loops are okay. And then you might already be ahead of me in noting that, what's T2 of 0, 0? This is also 0, 0. So not only are self loops allowed, but also you can have kind of multiple edges running between the same vertices. Right, so also, I think in the notes we call these parallel edges. I think they're often called multi-edges. So parallel edges are also allowed. And this doesn't really change any of our definitions of spectral expansion. And for the most part, it can be ignored, but I just wanted to point out that it is going on here. There are self loops and parallel edges, but it basically doesn't matter. I guess I should also note that kind of 0, 0 is a very degenerate case. It's going to end up mapping to itself. It maps to itself 4 times, and I think like to 1, 0 or 0, 1. So it doesn't look very expanding. It's very degenerate, but the rest of these will actually kind of be spreading out nicely. And I mean, in essence, we'll see this later in the proof. But okay, so any questions on the definition of this graph, which changed slightly midway through?
I mean, maybe one way to think about why this definition might make sense is basically these operations. I mean, they do not commute. So somehow the idea that if you apply them multiple times, you should move around this graph and never come back to where you started for some algebraic reasons. And if that's the case, then this should be an expander. I mean, maybe an example of a graph that's not an expander is, imagine you can like add 1, add 2, subtract 1, subtract 2, something like that, which is like, then the point is that if, I mean, there are tons of cancellations there. So this will not be a good expander. But here somehow the hope is that by doing this algebraic operation, that even though they're simple, they don't commute, then you should mix.
Right. So maybe another way to say this is kind of when you're not coming back means you're having very few short cycles. Right? So locally you kind of look like the infinite tree, which we talked about last week, is like the perfect expander. So somehow kind of we're taking advantage of this kind of algebraic non-commutative structure to build something that locally looks like the infinite tree. That's one way to think about it. Okay, so there's one kind of easy thing. We're gonna prove 2 things about the Margulis family of graphs. This lecture plus a little bit into next lecture. The first is very easy. The first I just want to claim that the Margulis graphs are strongly explicit. So Margulis family is strongly explicit. And this should be fairly obvious, right? Because we defined the edges with these operators. So if you ask me to give you the jth neighbor of V, I can just apply these operators. And V's description length is O of log n, and these matrices are just 2 by 2 matrices, with constant values in them, 1, 2, and 0. So I can just apply this into an O of log n time, give you the appropriate edge, right? So just compute edge using T1, T2, E1, E2, and the inverses, I guess. Right, so that's all you need to know, right? We're basically, by definition, these are already strongly explicit. So what's difficult is not proving that the family is nice and easy to construct. It's proving that it's actually an expander, a family of expander graphs. This is difficult. So the second one, and the main focus for this lecture and then part of the next lecture, will be the following theorem. So let maybe M equals Mn be the unnormalized. So it'll be a bit easier for us to work with the unnormalized adjacency matrix here. Be the unnormalized adjacency matrix of G equals Gn. Then I claim the following bound on the spectral parameter holds. Lambda m, which is the maximum of lambda 2 and lambda n, is less than or equal to, I believe the bound is 5 root 2. And notice that we're working with the unnormalized adjacency matrix. So remember, when you normalize, we want this to be less than 1. Right, it's strictly bounded away from 1 by a constant. Because we haven't normalized by the degree 8, we just want this to be strictly less than 8. And this is 5 root 2 is indeed strictly less than 8. So if we can prove this theorem, then you do get that the Margulis family of expander graphs, or of graphs, are indeed spectral expanders. Yeah, so I guess this is the main theorem that we'll be working on proving today. So I guess, yeah, okay. Probably no questions about things yet. Let's maybe first talk a little bit about how we're going to attack this problem. So the proof is kind of in 4 steps, in a sense, maybe 3 or 4 steps. Proof in, I'll say 3 steps. But then I'm cheating slightly because I'm going to call the first step 0. And what is step 0? Well, basically the overall idea of this proof is the same idea of like every proof that we've done in this class so far. We're going to look at the Rayleigh quotient and we're going to try to bound the Rayleigh quotient. Steps 1, 2, and 3 will be kind of, it turns out bounding the Rayleigh quotient is a little complicated. And we'll kind of break this down into a stepwise process. But before getting to that, let's actually go through step 0. Let's say formally, what do I mean? What do I want to bound with the Rayleigh quotient? What does the Rayleigh quotient look like for the Margulis graph? So let's talk about this first. This is kind of setup or step 0 of the proof. So first of all, let's just recall. And I'm cheating slightly in the sense that we proved something very similar to this, the kind of variational characterization of eigenvalues thing before we did Cheeger's bound, but it was a little different. But I claim that lambda m is equal to the maximum over functions orthogonal to 1 of the absolute value of the Rayleigh quotient of f transpose m f over f transpose f. And this is proved exactly the same way as the lambda 2 characterization that we did earlier in the class. So I'm not going to go back through it. It's like literally the same proof, just put in absolute value instead of not having absolute value, and you'll get this. So in other words, what do we want to do? We want to bound the maximum absolute value of the Rayleigh quotient of functions f orthogonal to all 1 vector. Right? Okay, so this should be a familiar technique at this point. So the first thing I guess I want to do is write out a little bit more, expand out the Rayleigh quotient a little bit more explicitly. So in particular, kind of writing out the definition of the unnormalized adjacency matrix, we can kind of equivalently write this out as we want to prove the following bound. We want to prove, so kind of the numerator here is going to end up being 2 times the absolute value. So we can sum over, the adjacency matrix gives us a sum over edges, right? So we get a sum over kind of U, V in the edges of the Margulis graph of FU, FV. This is just straight from the definition of the adjacency matrix. And we want to prove that this is less than or equal to 5 root 2 times F transpose F, which is the sum over the vertex set, which remember is Zn squared of F of Z squared. Let's just move the 2 over to the other side. So we've got 5 over root 2. Okay, so this is just a restatement of the same thing. If we can prove this bound here, we'll be done. And I want to kind of expand this one more step. So I have this sum over edges, but for the Margulis graph, we know exactly the edges, right? They're defined by these affine operations. So we can go ahead and write it out as a kind of a sum over vertices and the things that vertices are connected to, rather than a sum over edges. And this will be a little bit easier to analyze. This is the format we're going to want it in for actually getting the bound. And so what does this look like? Well, okay, so I'm claiming that there's an equivalent goal is the following, which is just expanding out the left-hand side. So I have a sum now over kind of vertices over Z and Cn squared of what? Well, we'll have Fz, and then we'll have the things that Fz is connected to. So we'll have kind of just looking back at the definition of our graph, we'll have Ft1z, we'll have Ft2z, we'll have Ft1z plus E1, and we'll have Ft2z plus E2. And I'll note, so I've only included 4 out of the 8 edges here, right? Which is kind of what you would expect, because if we summed over all 8, you would be hitting every edge twice, right? So I could have written out all 8 edges and then written half in front of it. But instead, what's a little bit easier is to write out kind of just the first 4, and note that this sum will also hit the, I missed an absolute value here. The sum will also hit the inverse operations. So when we look at a different Z, right? So when will we hit like T1 inverse Z? Well, when we input, when Z here is actually equal to, say, T1 inverse Z, what will happen to this term? Well, we'll end up getting F of T1 inverse Z, and then this term will become F of Z. So basically, kind of later in the sum, you're going to get the remaining edges connected to F of Z. So each of these will still hit the 8 edges. This is just a slightly simpler way to write the sum. If you don't believe me, maybe stare at it a little bit after class. So that kind of you just get from the inverse operations, you end up getting all of the edges. So this is an equivalent way to write out this. So these are equivalent, right? So equivalently, our goal is to prove this bound. So what would we do, kind of given past what we've done in the past? What's kind of the main strategy to use here? Well, the most obvious thing to try would be to use Cauchy-Schwarz, right? So this sum here, this sum on the left-hand side, this is basically 4 inner products, right? This is the inner product of F with an affine shift by T1, or a shift by T1, linear map by T1, by T2, and then affine shifts here. So we could define these as inner products, and we could take Cauchy-Schwarz, and this would indeed get a bound. But the problem is that if you try to apply Cauchy-Schwarz, what bound would you get? Well, each of these terms, so each term would give you kind of a sum of F squared of Z. So each term would give sum of F squared Z. So you'd end up with for sum of f squared z. And what bound would this then imply on the expansion? Well, you get that lambda g was less than or equal to 8. But we're in an 8 regular expander graph, right? So we're in an 8 regular graph. This is lambda 1. So this is too weak. Cauchy-Schwarz will not prove that this family is expanders. It gives, we already know that lambda 2 through lambda n is less than or equal to 8, right? All of the eigenvalues are between 8 and -8. So this is totally unhelpful. It's a trivial bound. It tells you nothing, which is a little bit problematic because it's one of the only tools that we've used so far to analyze this sort of thing in the course. So what in the world are we going to do? We're kind of stuck. And so what we're going to do is kind of appeal to something called Fourier analysis, and this will be step 1. So we're going to kind of rephrase the theorem in terms of what's called Fourier analysis. And let me just note, I guess for people who haven't seen Fourier analysis, this is fine. You don't need any background in Fourier analysis for this lecture. We'll cover everything that you need to know. So basically, and maybe Shahar will jump in and correct me here, but I think the simplest way to think about Fourier analysis is that you have kind of these functions, and what you want to do is find like a really nice basis for these functions. I'm going to tell you about the basis in just a second, but basically we're going to find this basis of functions that we can kind of compute and act nicely with respect to each other. They're going to be orthonormal. And this is going to kind of make things really easy to reduce to something we can actually analyze. And kind of overall, that's all that's going on. We're really just finding a really nice change of basis to then massage things into a form that we actually kind of know how to deal with. That's the overall idea. I guess I'll just also mention, because the language differs a little bit, if you're from the math community and you know representation theory, this is basically just representation theory. The language is different enough that like it's possible to know both and not realize they're the same. So which actually happened to me for like a month or something when I was first learning about this. So worth noting, if you know representation theory, this is just kind of finite abelian group representation theory. Anyway, let's actually move on to
Next, let me just add one thing.
Yeah.
So you're talking about Cauchy-Schwarz. So one place where Cauchy-Schwarz would be tight would be if there were, let's take all these elements like T1z, T2z, and then T1z plus C1, T2z plus C2. Let's say that all of them had like some orbit. Let's say they would never escape, right? Let's say you could take all your elements and all your vertices and partition them into sets so that each operation only acts within the set. Then such a graph will never be an expander, it's not connected, but also the Cauchy-Schwarz would be tight because you can choose f to be constant on each part. And the whole point of being an expander is that this should not happen. So really what you want to say that these things never give you the same thing. You cannot choose f in some consistent way that you all get the same value. Things must be uncorrelated to each other, so you can do better than Cauchy-Schwarz. And really Fourier analysis, and like you said, this change of bases will give us a more convenient way to analyze and show that things are not correlated. Yeah.
Nice. I guess so. Before I move into Fourier analysis and some background, I guess I should. It's a good time to pause. Are there any questions on the setup? So we're just trying to upper bound the Rayleigh quotient, or the definitions we've gone through so far. Okay, if not, then we'll get into Fourier analysis. Okay, so I've told you that we're basically finding this this nice basis. So let me maybe start off by telling you kind of what the basis functions look like, and then a little later I'm going to state kind of the main theorem that we won't prove in Fourier analysis, which is basically that these things actually give a really nice basis. But to start off, let's just kind of define the objects. So these are called characters. And we'll say, okay, given a finite abelian group H, and just I guess as a reminder, I won't fully define what a finite abelian group is, but basically this is just some kind of set with some sort of operation that acts nicely. And an abelian just means that kind of for all s prime in S, we have that S composed with S prime is equal to S prime composed with S. So this is true for many things like addition mod n, for instance. So this is true for our Zn squared. It's not true for things like matrices, right? When you flip matrices, they don't necessarily commute. So this theory becomes much more complicated when you're not over a finite abelian group. Anyway, it won't matter that much to us for now, but just wanted to mention this. Okay, so we're over some finite abelian group. A function, we'll call it chi, mapping from the group to the complex numbers without 0, which is denoted C star. This is like the multiplicative group on the complex numbers, is called a character if it satisfies the following relation. For all x, y in H, basically we want that chi kind of preserves the group operation, kind of preserves addition over to multiplication on C star in the following sense, that if we apply chi to x plus y, it will be the same as if we applied chi to x and then apply the operation on the right-hand side, multiply. So it's the same as if we apply chi to x, and then we multiply by chi of y. So really what this is saying is something about kind of preservation or some kind of nicely acting with the operation plus on the left-hand side versus times. So plus, which is defined with respect to H, maybe I should say plus here, since we'll be using Zn squared and plus will be kind of our operation. So basically it respects this operation moving between H and C star. So this, if you haven't studied algebra before, you should think of this as basically being analogous to linearity. So because we're not over vector spaces, kind of linearity isn't the right thing to talk about, but it's the same type of property. And generally this is called like a group homomorphism. But just think about it as some kind of linearity or niceness condition on the function. Okay, so that's a character, basically just a group homomorphism. And let me give some examples of, this is maybe general and abstract and unclear, so let me give a few examples of characters. Okay, so the first example is called the trivial character. And this is a character for all groups, for all finite abelian groups. I guess actually just for all groups. And this is, we're going to denote it by chi 0. And it's just defined to be 1. It's just the constant function. It's 1 on everything. So why is this a character? Well, chi of x plus y is equal to 1, because everything's equal to 1. But 1 is equal to 1 times 1. And that's equal to chi x times chi y, right? Because these are both equal to 1. So this is, I'm not saying anything, crazy here. This is totally trivial. Everything's 1, and 1 times 1 is 1. So this is a character. You might think that this is kind of useless, and I'm not saying anything interesting, but in fact, it will actually be important for us, namely because it basically takes, once we move over to Fourier space, it takes the place of like the lambda 1 of the constant function and the corresponding top eigenvalue. So this actually will be important. I'll say a little bit more later about what I mean. Okay, so the first example is the trivial character. Now let's look at it. Let's look at the characters of a very simple group. So maybe H equals Z mod n. What are the characters of H equals Z mod n? These will basically be given by kind of nth root of root of unity calculations. What do I mean by that? Well, this will end up being kind of the family chi a, for a lies in Z mod n, so in 0 through n minus 1. And we'll define chi a. This will be, or let's say maybe chi a of x will be equal to omega to the ax, where what is omega? Where omega is an nth root of unity. So in particular, let's just let omega be 2 to the, e to the 2 pi I over n, right? So this is something where when you raise it to the nth power, you get 1. E to the 2 pi I is equal to 1. Okay, so it should be maybe somewhat intuitive what's going on here, right? We want this to be kind of something exponential, because we want that when we product things over here, that it looks like summation on the other side. And so kind of e raised to something is a natural choice. Let's maybe spend a little bit to see why we picked why did we pick these roots of unity? I won't prove to you that these are all the characters, but let me at least prove to you that they are actually characters. Since I think it's maybe useful to see to kind of get an idea of what's going on. So let's just compute chi of x plus y, right? So what is this equal to? Remember that this is done mod n, right? This is addition over the group, which means it's addition mod n, kind of just implicitly. So what is this equal to? This is equal to e to the 2 pi I a times x plus y mod n divided by n. And the trick here is to note that kind of this is cyclical, right? It's a nth root of unity, and so I can kind of add in here. I can add in here any number of copies of n as I want, and it won't change anything, right? I'm just multiplying by e to the 2 pi I, which is adding, multiplying by 1. So in other words, I can kind of add cn as much as I want. In particular, x plus y mod n, like I can just add n's until I actually get to x plus y, right? Like if maybe I have n plus 2, then I can just add 1 copy of n to actually get to the exact value of x plus y. So anyway, this is just to say that this is equal to x plus y not mod n, right? Basically because this is an nth root of unity, the mod doesn't make any difference at all, right? So this is equal to e to the 2 pi I a x plus y over n. And just by definition, this is chi ax, chi ay. And that's the relation, that's the only relation we had to prove for it to be a character. So it's possible to prove that these are the only characters. I think it maybe takes a little bit of algebra, but it's a reasonably nice exercise if you want to go look at it to kind of understand characters. But I won't do it here because it's not really our focus. So the third example, which is maybe less of an example of something that's actually quite important to us, is the characters of Zn squared, right? The group that we actually care about in the Margulis construction. So what are the characters of Zn squared? Well, they're basically just what you would expect. They're like kind of products of the characters of Zn. So this is a Cartesian product. You could have ended up with the products. I won't prove why exactly you get this, but again, it's a nice exercise if you want to go work it out. So in this case, we get chi. So these are indexed by tuples, where AB lies in Zn squared. And you can probably guess the definition here without me even telling you. Chi AB of xy is equal to omega to the ax plus by. So I've just producted the characters chi a and chi b. And I won't prove to you the proof that these are characters is, I think, similar. I'm not gonna go through it again. But it turns out that these are exactly the characters of Zn squared. There are no other characters. And this is, I guess, all of the examples that I wanted to go through. So the next thing to state is kind of the main theorem, the fact that these characters actually form an orthonormal basis. But before that, I just want to check, are there any questions on the definition of character or on these examples that we looked at? Okay, if not, then let me state kind of the main theorem in Fourier analysis that we will be kind of appealing to, which is just that the characters form an orthonormal basis for the space of functions that we're over. So let me state this a little bit more formally. I'm just going to call this the character basis theorem. I couldn't actually, Shahar, do you know, is there a name for this in the literature? I tried to look, but couldn't actually find it.
No.
It's a really important theorem, so I was kind of surprised that it wasn't named.
I agree. I mean, yeah, I don't know the name for it. Yeah.
Yeah, well, I'm just going to call it the character basis theorem because it didn't seem to be kind of named anywhere. And what does this say? This says if, let H be a finite abelian group. First of all, H has size of H characters, exactly. So this is what we saw up here, right? Zn had characters indexed by Zn. Zn squared had characters indexed by Zn squared. And we'll write them as kind of denoted, as we did in the examples. These will be denoted as chi y, for y lies in the the group. This is how we denoted them above. So that H character is denoted like this, and they form an orthonormal basis for the space of functions, F mapping from H to the complex numbers. And I should say, I'm talking about an orthonormal basis. I better define an inner product with respect, orthonormality is defined with respect to some inner product. So orthonormal with respect to what? Well, with respect to kind of the standard normalized Hermitian product. So with respect to the following Hermitian product, Fg is equal to 1 over sides of H, so it's normalized. Sum over, let's say, X and H of Fx bar, Fx conjugate, Gx. So this is basically the standard Hermitian product. I've normalized it, but hopefully you've seen this in maybe a linear algebra class. If not, it doesn't really matter. I guess just take on faith that this is Hermitian product, and that this is an orthonormal basis. This is kind of the main theorem. I'm going to tell you in a minute. I guess it's not immediately clear why this is useful. It's some sort of orthonormal basis for functions. I'm claiming that what we're going to do is we're going to decompose F into this basis, and then kind of magically this is going to make things nice, and that's going to be what the rest of the lecture and part of Thursday will be, is showing that this is indeed true. So I guess I want to mention kind of 3 really useful corollaries of this theorem, and hopefully these ones we can actually kind of at least assuming that the theorem, we'll actually see more or less the proofs of these, or see why they're true. So I want to say kind of 3 corollaries. So the first one is just that this is hardly a corollary. This is basically just the definition of an orthonormal basis. But so F from any function F from H to C has a decomposition into the characters because it's a basis. Decomposition. F is equal to the sum over let's say X in H of F hat X, so some coefficient times a basis vector, chi X. Okay, so this is just from being a basis, right? And because the basis is orthonormal, moreover, you can, so okay, maybe I should say this is called the Fourier decomposition. And this is called the Fourier character. Sorry, the Fourier coefficient. So if you want to know what something is called in Fourier analysis, just take what it would normally be called and then put Fourier before it, and you'll be right 95% of the time. So this is the Fourier decomposition and the Fourier coefficients. And then the nice thing is that because this is an orthonormal basis, we can actually explicitly compute these coefficients just by taking an inner product, or Hermitian product. So in particular, this F hat of X is just equal to the inner product of F with chi X, which by our definition of the inner product is what? Well, this is 1 over H of the sum over, maybe let's see, Y in H of F bar of Y chi X Y. So this is just from, this is basically immediate from orthonormality and being a basis.
I think to actually get that, you need to put the conjugate on the other side. Otherwise, you get F conjugate Y. Or F conjugate X.
Wait, so you want to take the conjugate of the character?
No, I'm saying that. See, what do you have here? So you have here Fy, chi xy, inner product with chi x, and no. First of all, the equation you wrote here is not correct. So you want to keep doing. So you want to decompose F and then do this inner product with chi x.
Yeah. So F should be equal to some F hat X chi X, and then this is inner producted with chi X.
Maybe let's not use the same X.
That's a good point. y.
Okay. Then the way you define inner product, you conjugate the first element, the first term, right?
Yes.
So you'll get the conjugate of f hat y. So I think to actually get it, you want to, in the inner product definition, you want to conjugate the second term, not the first.
Huh. Okay, I think in the notes we did the first term, so maybe that's an error in the notes.
So then it should be chi-x inner product f. Oh, we had a typo.
Yeah. Okay. I think Shahar is right. Maybe we'll fix this in the notes after. So you want to conjugate, but you still want to keep the definition.
It doesn't matter.
Yeah, it doesn't really matter. Okay, we'll just write this as chi-x f. I think something might be slightly flipped in the notes. We'll fix this after class, I guess. Okay, regardless, this is what you should get if you expand out this this form. I mean, this should, right? The idea is that all the chi-y, chi-x terms are zero because it's orthonormal. So this should end up getting you yeah. So this would in fact give you f hat bar as Shahar is saying. So what this would give you is f hat y chi-x, which is equal to the conjugate of f hat.
Yeah, but I think also it's a standard way of doing conjugation over C that you conjugate the second term, not the first term.
Yeah, it is. I was just trying to follow the notes, which had it as the first term.
But they're not so mistakes.
We'll fix this, but yeah, you do technically want to conjugate the second term. I guess I'll. It shouldn't really matter, so I'm maybe gonna stick for now with the notation that I have in the notes, but we'll fix it next class or soon. It doesn't really matter which side you conjugate. This is just kind of notational, and things are equivalent. Okay. Anyway, so the point I wanted to make is just that f has this decomposition. So the corollary number 2 that I wanted to mention is so I've said before that the trivial character will actually be important. So why? Well, it turns out that kind of so f hat of the trivial character is always denoted chi 0. And remember that this is like equivalent to 1. And so why is it important? Well, it turns out that f being orthogonal to 1, the original function f over in normal space before we've kind of taken the Fourier decomposition, this is equivalent to f hat of 0, the coefficient of the trivial character, being equal to 0. And this just follows immediately from 1, right? Because what is this? What is f hat 0? It's just the inner product of the all ones function with f. And so this is equivalent to being orthogonal to 1. There's maybe something here to be said about conjugating, but basically this is all it is, right? It's defined as being the inner product. So this being 0 is exactly equivalent to, in non-Fourier space, f1 being equal to 0.
Actually, here conjugation doesn't really matter because the 1 is a real function.
Yeah.
So 1 conjugate is 1.
Yeah, f is a real function. So yeah, conjugate doesn't
matter. It doesn't matter about f, just that 1 is a real function.
Sure. Okay, the third thing that we'll need to know is called Parseval's theorem. And this is basically just a way to translate between f in the original basis and functions in the Fourier basis when you're inside an inner product. And because the things that we're looking at currently are basically a bunch of inner products, this will be very useful to us. This is actually how we're going to move between standard land and Fourier land. Right, so in particular, what is the theorem? Well, it says that fg is equal to just this normalized inner product of the Fourier coefficients of f hat, g hat. And I won't go through the calculation, but the proof is just kind of, decompose f and g by 1 and simplify by orthonormality. So I'll leave this as an exercise, but if you kind of assume the main theorem and this is an orthonormal basis, it's pretty much immediate from definitions that this is true. This is how we'll kind of move between our two languages. So I guess any questions on the theorem that we're just assuming the proof of, or any of these corollaries that should be maybe a little bit more clear? All of these basically are just following from definition and orthonormality. So questions, I guess, so far on the Fourier background. This is most of the background we're going to need. There's kind of one more thing, but mostly this is all we need. Okay. Let's look at then. Let's keep some of this up maybe. Let's look at then how to actually let's kind of take our original statement and let's transfer it into Fourier language, and we're going to make an equivalent theorem to prove over this other basis, this nicer basis that we're claiming we'll actually be able to work over. So let's start by recalling the original goal, because it was a while back, or maybe not original, but kind of the last step that we were previously at. We wanted to prove the following bound, right? We wanted to bound the sum. So this sum is always over Zn squared. The sum of Fz times what? These kind of its affine shifts, right? T1z, T2z, T1z plus E1, T2z plus E2. And we wanted to prove this was less than or equal to, I think, 5 over root 2 times the sum of f squared x. Okay, so let's rephrase this a little bit and then apply Parseval to move it over to kind of the Fourier domain. So it'll be, we don't have to do this, but it'll be convenient to kind of label each of these as a different function. As kind of, these are affine shifts of f, essentially. Let's just call them something else for notational simplicity. So in particular, kind of, we'll call this G1, we'll call this G2, we'll call this G11, and we'll call this G22. Let me say it a little bit more formally. So define Gi of z is equal to f of ti of z, and Gii z is equal to f of tiz plus ei. We're just defining some notation to make things a little bit, massage things into kind of the form that is more familiar. So we can rewrite now this inequality, at least the left-hand side. We can rewrite this as this just four inner products, right? So okay, our inner product is normalized, so we maybe need to pull out a size of the group, which is n squared. So we need to pull out an n squared, but otherwise we just have f with G1, right? This is this first term. We have f, similarly f with G2. We have f with G11, and we have f with G22, right? I've just restated, I've just moved to a different form. I haven't done anything here. Over here, the equivalence, again, we have an n squared that gets pulled out, and this is ff, right? So, okay, what did we just have with Parseval? Well, we had an exact relation between fg and f hat g hat, right? So now we can transfer over to Fourier land using Parseval's identity. Okay, so this is equivalent to the following. Again, we pull out another factor of n squared. Both sides are going to get normalized by the same factor, so this doesn't really matter. So now the only difference is that these are now wearing hats. So these are now the Fourier coefficients. G11 hat plus f G22. And then we're also going to take Fourier coefficients of the right side. 5 over root 2 n to the fourth, f hat. So these n to the fourths cancel, right? Okay, so now we have things in terms of Fourier coefficients. And our goal is somehow to massage the left-hand side here into the form of the right-hand side. And what's the problem with doing this? Well, on the left-hand side, we have these g hat i's. And it's a priori, it's not really clear what to do with these. We want them to be in terms of the Fourier coefficients of f, because we want everything to be in terms of the Fourier coefficients of f, so we can get at this f hat term. And thankfully, so here's kind of the last piece of background we're going to need. Basically, because the GIs are just affine shifts of F, you can in fact compute the Fourier coefficients of G in terms of the Fourier coefficients of F. And I'm just going to kind of state the claim here. I'm not going to prove it for you. But so I claim kind of that there's a very simple way to transfer between these. So namely, let's maybe let G be G of Z be some function where this is basically an affine shift of F. So this is equal to F of AZ plus B, where A is invertible, is non-singular. Then I claim that the Fourier coefficients of G are basically kind of a transformed version of the Fourier coefficient of F based on A times some kind of shift by a root of unity, by some kind of omega to the something term. And in particular, it looks like this, and you can go verify it if you want on your own. But basically, G hat of X will be equal to I think it's omega to the negative inner product of A inverse B comma X. Let me just double check that I'm not lying to you. Yes, that's correct. F hat A inverse transpose times X. Okay, so like I said, I'm not going to prove this, but I think you should be able to kind of work through this with the definitions if you want that we've given you.
Actually, I think that's a good exercise. I mean, I think for people who are unfamiliar with Fourier analysis, and if you want to make sure that you understand the definition, this just follows the definitions. I mean, there's no deep math going on here. You just plug in the definition of the Fourier coefficients, and you work with them. You should be able to get it. So I think you should all try to do it. And if you don't succeed, then tell us, and we can give you some hints on Piazza. But I think that's a good exercise to try and do.
Okay. Yeah. So yeah, especially if you haven't seen Fourier analysis before, this is like Sarah said, it's just an exercise of working through the definitions, which is always helpful to understand what's going on. Okay, so I guess I want to note one more thing, which is that in our case, A is going to be equal to T1 or T2, right? And because T1 and T2 are transposes, we'll have that T1 inverse transpose is equal to T2 inverse, and T2 inverse transpose is equal to T1 inverse. So everything will basically just be in terms of T1 inverse, T2 inverse, instead of having transposes floating around. So I just wanted to note this up front, because we're going to use it kind of throughout. It's just a useful fact. So let's now actually use this fact to rewrite. Let's now rewrite this left-hand side. First of all, I guess for simplicity, just note we can write this as F hat with G hat 1 plus G hat 2 plus G hat 1 1 plus G hat 2 2, right? This is equivalent. Okay, so let's maybe write this out. So what is this? Let's go back to some formation. Okay, so I'm going to maybe drop a normalization factor. Both sides are going to get normalized by the same factor, so bear with me. So what is this? Well, this is the sum over Z in Zn squared, and I'm now actually going to write out that this is equal to Z1 comma Z2, because these terms are now going to be important basically because of this shift. So what is this? Okay, well, this I guess again depends on how you define your Hermitian product, but for now let's use the one where the first term is what's conjugated rather than the second term. So you end up with F hat X bar, and then so G1 and G2, B is 0, right? So the first one's B is 0, which means
F of Z, right? Not X.
Yes, thank you. F of Z. So in the first two terms, G1 and G2, there's no shift. So this omega term is just 1. So what do we get? Well, we're just gonna, and we have these transpose relations, right? So the transpose basically dies. So what we get is just F of T1 inverse Z and F of T2 inverse Z. And then
F hat.
Yes, F hat, thank you. So what do we get for the affine shift terms? Well, let me just kind of claim what it is, and then I'll briefly explain why. I claim that this is kind of omega to the negative Z2, F of T1 inverse Z, and omega to the negative z1 of f of t2 inverse z. You'll notice that, so this is two, kind of the 2 and 1 are flipped here. Like the coefficient out front is z2, inside we have t1. The reason for this is the transpose here, right? Which is basically flipping between 1 and 2. And why do we get like, why do we get
instead of hat?
Yeah, every time it should be f hat. Thank you. Apparently I don't like drawing hats. Yes, these should all be f hats. We're in Fourier land now. Soon I'll just define something to be f hat so I can stop writing hats. But at the moment, we're still writing hats. So maybe let me explain kind of this term, this last term here. The previous one is the same. So how are we getting this? Well, remember this is kind of omega to the negative, I guess t1 inverse e1 10 x times stuff. So what is t1 inverse 0? So let me just write this out. T1 inverse 10 is equal to, so what's t1 inverse? I think it's 1 negative 2 0 1 just by direct computation. So 10, this is just equal to 10, right? So in particular, when you apply this to x, which I maybe should have written as z, you get z1 out. You get the first coordinate out. So this is where the z1's coming from. Then you have t2 here because you take the transpose of the inverse matrix, which gets flipped you from t1 to t2. So that's where these terms are coming from. I was maybe a little fast. If you didn't follow, it's just, it's just literally plugging things into this claim. You can look it over if you don't believe me at the moment. Okay, so maybe we have 8 minutes. How much could we go through? Let me kind of state. So this is actually basically the end of step 1, which is kind of rephrasing things in terms of Fourier analysis. So maybe let me kind of state the equivalent version of the theorem over in Fourier analysis land to the one we were originally, to like our very original goal that we were trying to prove, or at least kind of a sufficient thing to prove. So I'm finally going to get rid of the hats because apparently I can't write them. So let's just define kind of capital F to be f hat. So we'll be thinking about capital F as kind of little f just over in the Fourier domain. And I want you to recall that we had this useful corollary where kind of f being orthogonal to 1 was equivalent with kind of f hat equals f of 0 as being 0. So remember that we're trying to look at the Rayleigh quotient of everything that's orthogonal to 1. So over in the Fourier domain, this is equivalent to looking at functions where f0 is 0. So in particular, kind of the Fourier version of the theorem that I now want to prove is the following. For all functions f from zn squared to c, to the complex numbers, maybe such that f of 0, 0 is equal to 0, I want to prove the following bound. I'm just going to simplify this a little bit. I want to prove that the sum, again, over z lies in zn squared, maybe let's write this out as z1 comma z2, of what? Of fz bar.
Max, can you scroll the screen a bit up? The zoom bar on the bottom is hiding what you're writing here.
Oh, you're right. It's not hiding into my screen. Thank you. F bar of z times f of t1 inverse z. So just collecting the terms above, this is 1 plus omega to the negative z2 plus f of t2 inverse c 1 plus omega to the negative z1. And I want to prove that this is less than or equal to 5 over root 2 sum of f of z squared. So I've also taken the right-hand side over to the Fourier domain. So remember up above we had kind of f hat. So I'm just writing this out. This is the absolute value of f of z squared. Okay, we only have 5 minutes, which means we definitely cannot finish the second step. I guess let me just give you a taste of kind of where we're going, and then we'll finish. So just because kind of as is, it's still kind of really unclear, at least to me. It's still really unclear what to do with these. So let me give you kind of the first step of part two, and then we'll finish it on Thursday, which is just to say, I just want to, okay, notationally, so notation, it'll just be a little bit simpler to let GZ be defined to be the absolute value of f of z. Because we'll mostly be working with absolute values. And then there's a very useful relation that maybe you've seen before. There are these relations between roots of unity and sines and cosines, right? There's somehow these very interesting kind of Euler relations between roots of unity and trigonometry. And in particular, I won't prove this, but recall that kind of the absolute value of 1 plus omega to the negative t is actually equal to 2 times the absolute value of cosine pi t over n. So this is maybe why, at least hopefully should give you some kind of intuition of how we're eventually going to get this to some form that we can analyze. In particular, we can kind of move from this weird complex form, and we can kind of take absolute values until we get to some statement about cosines. And then basically, we're just going to be able to kind of term by term evaluate what's going on with these cosines to prove the theorem. So let me maybe just give kind of one full version of, one further simplified version of what we want to prove. So let's look at this term, and I'll just call this left-hand side for simplicity. And so I claim that by the triangle inequality, the left-hand side is less than or equal to the following, just applying triangle inequality plus this useful relation. It's less than or equal to the sum of 2gz g of t1 inverse z times cosine of pi, I think z2, pi z2 over n, plus g of t2 inverse z cosine of pi z1 over n. And remember, what do we want to prove? So it's enough to prove, we have enough to show that this is less than or equal to 5 over root 2 times the sum of gz squared. Right, so I won't go past this point, but somehow we've massaged things to be a little bit simpler. Now it's some statement about cosines. We still have this problem where on the right-hand side, we have these gz squareds, and on the left-hand side, we have kind of these cross terms. We have these gz, g, and then shifted z. And I don't have time to talk about how to fix this yet, but again, Cauchy-Schwarz won't work out. It'll still be too weak, even though we've shifted over to the kind of Fourier domain. But there'll be a nice trick with kind of looking at cross terms versus squares that will let us analyze this in a better way. And I'll talk about that on Thursday, and we'll finish up the proof. But I think I should probably stop for now because I don't have time to go through anything more substantial before the end of class.
Let me just add one comment of what maybe now it's a bit clearer why Fourier analysis was used. But Fourier analysis, like Matt said, is just finding like an equivalent form of the inequality we're trying to prove by changing basis. But the thing that happened here is that suddenly we see that this notion of not being correlated is actually captured by these cosines not being very close to maximal. So we'll see that coming up later. So these cosines act as phases of this g and how they correlate to each other. And we see that basically what we're going to show is that these cosines are going to break the correlation. They're not going to be close to 1 almost always. They can't be if z1 and z2 are not very close to 0. And that would allow us to prove that things are not correlated, which allow us to show that to do prove things which are stronger than what you just get by Cauchy-Schwarz that ignores these correlation issues.
Right. So we still can't apply Cauchy-Schwarz here blindly, but now we kind of don't need to because we have exactly these cosine terms, which will help us do work.
Yeah, I guess another thing is that the condition of being orthogonal to 1 got simplified to just being 0 at 0. So just a simpler condition to work with.
So I guess I'll stick around for questions for a bit, but that's the end for today.
I have a question.
Mhm.
Suppose we change the matrix T1 for the definition for this graph. Is this into 1101 instead of 1201? Is it still expander?
What would happen if you did that?
But I think there are two questions. One, is it still an expander? And the second one, would the same proof work? So in general, for these algebraic constructions and for related ones, there's something called the 1, 2, 3 conjecture of Lubotsky that says that basically any construction like that could work. I mean, unless there's an obvious reason, like an obvious algebraic reason why it should not work. Let's say your matrix T1 and T2, commute or something like that, then it should work. And it took a while. I think at this point it is known to be true, or it's known to be true in many cases, but the proofs there are very algebraically heavy. And the nice thing about the proof that Max is showing you now, this Gabber-Galil proof, that it works only for specific parameters, but we don't use any heavy algebra. So I don't think the Gabber-Galil proof would work for any range of parameters. The algebraic proofs would work, but first of all, they're much heavier, and also sometimes the original Margulis proof did not prove any quantitative bound. They just proved this bound is less than 8. It did not prove any concrete constant. So, but yeah, I mean, in principle, it should work, but not with this type of elementary proof.
I see. Also, I think there is a name for the character orthogonality theorems.
Oh, what?
So it's called Schur. Yeah, it's Schur orthogonality.
Yeah. Like Schur's. Well, okay, Schur's lemma is going to be something different, but that does sound right. Yeah.
But I think Schur's things came after Fourier analysis. So Schur is really taking Fourier analysis and generalizing it to non-abelian.
Schur is the representation theory.
Yes, representation theory, which it is true. Fourier analysis is a special case of it, but it came after Fourier analysis. I mean, Fourier analysis was invented by Fourier. So I don't know if it's fair to call this like Schur lemma.
Yeah.
But I get point.
The Schur thing, the Schur orthogonality does generalize the orthogonality of characters.
Right.
But I think just one comment, I guess people are leaving, but I guess even if you didn't follow this Fourier analysis, you could just start with this formulation next time, and then just say, take it on faith. This is what you get for Fourier analysis. It's equivalent, and then start.
Yeah, we'll make the next work. We'll make the next lecture self-contained with that for that Fourier analysis. I think.
Yeah. So maybe I'll stop recording now.